An intuitive explanation of Bayes' theorem, Part 4. E. T. Jaynes, in probability theory with applications in science and engineering, suggests that credibility and evidence should be measured in decibels. Decibels? Decibels are used for measuring exponential differences of intensity. For example, if the sound from an automobile horn carries 10,000 times as much energy, per square meter per second, as the sound from an alarm clock, the automobile horn would be 40 decibels louder. The sound of a bird singing might carry 1,000 times less energy than an alarm clock, and hence would be 30 decibels softer. To get the number of decibels, you take the logarithm base 10 and multiply by 10. Decibels equals 10 log base 10 intensity. Intensity equals 10 to the power of decibels over 10. Suppose we start with a prior probability of 1% that a woman has breast cancer, corresponding to an odds ratio of 199. And then we administer 3 tests of likelihood ratios 25 to 3, 18 to 1, and 7 to 2. You could multiply those numbers. Or you could just add their logarithms. 10 log base 10 1 over 99 is approximately equal to minus 20. 10 log base 10 25 over 3 is approximately equal to 9. 10 log base 10 18 over 1 is approximately equal to 13. 10 log base 10 7 over 2 is approximately equal to 5. It starts out as fairly unlikely that a woman has breast cancer. Our credibility level is at minus 20 decibels. Then 3 test results come in, corresponding to 9, 13, and 5 decibels of evidence. This raises the credibility level by a total of 27 decibels, meaning that the prior credibility of minus 20 decibels goes to a posterior credibility of 7 decibels. So the odds go from 199 to 5 to 1, and the probability goes from 1% to around 83%. You are a mechanic for gizmos. When a gizmo stops working, it is due to a blocked hose 30% of the time. If a gizmo's hose is blocked, there is a 45% probability that prodding the gizmo will produce sparks. If a gizmo's hose is unblocked, there is only a 5% chance that prodding the gizmo will produce sparks. A customer brings you a malfunctioning gizmo. You prod the gizmo and find that it produces sparks. What is the probability that a spark-producing gizmo has a blocked hose? What is the sequence of arithmetical operations that you perform to solve this problem? 45% by 30%, over, 45% by 30% plus 5% by 70%. Similarly, to find the chance that a woman with a positive mammogram has breast cancer, we computed P, positive given cancer, XP, cancer, over, P positive given cancer XP cancer plus P, positive given not cancer, XP, not cancer. Which is P, positive, cancer, over, P, positive, cancer, plus P, positive, not cancer. Which is P, positive, cancer, over P, positive. Which is P cancer given positive. The fully general form of this calculation is known as Bayes' theorem or Bayes' rule. Bayes' theorem.
P a given x equals px given a, xpa, over px given a, xpa plus px given not a, xp not a.
When there is some phenomenon A that we want to investigate, and an observation X that is evidence about A, for example, in the previous example, A is breast cancer and X is a positive mammogram, Bayes' theorem tells us how we should update our probability of A, given the new evidence X. By this point, Bayes' theorem may seem blatantly obvious or even tautological, rather than exciting and new. If so, this introduction has entirely succeeded in its purpose. Bayes' theorem describes what makes something evidence and how much evidence it is. Statistical models are judged by comparison to the Bayesian method because, in statistics, the Bayesian method is as good as it gets. The Bayesian method defines the maximum amount of mileage you can get out of a given piece of evidence, in the same way that thermodynamics defines the maximum amount of work you can get out of a temperature differential. This is why you hear cognitive scientists talking about Bayesian reasoners. In cognitive science, Bayesian reasoner is the technically precise code word that we use to mean rational mind. There are also a number of general heuristics about human reasoning that you can learn from looking at Bayes' theorem. For example, in many discussions of Bayes' theorem, you may hear cognitive psychologists saying that people do not take prior frequencies sufficiently into account, meaning that when people approach a problem where there's some evidence X indicating that condition A might hold true, they tend to judge A's likelihood solely by how well the evidence X seems to match A, without taking into account the prior frequency of A. If you think, for example, that under the mammography example, the woman's chance of having breast cancer is in the range of 70% to 80%, then this kind of reasoning is insensitive to the prior frequency given in the problem, it doesn't notice whether 1% of women or 10% of women start out having breast cancer. Pay more attention to the prior frequency is one of the many things that humans need to bear in mind to partially compensate for our built-in inadequacies.
A related error is to pay too much attention to p, x given a, and not enough to p x given not a, when determining how much evidence x is for a.
The degree to which a result x is evidence for a depends not only on the strength of the statement we'd expect to see result x if a were true, but also on the strength of the statement we wouldn't expect to see result x if a weren't true. For example, if it is raining, this very strongly implies the grass is wet. P, wet grass given rain, is approximately equal to 1, but seeing that the grass is wet doesn't necessarily mean that it has just rained. Perhaps the sprinkler was turned on, or you're looking at the early morning dew. Since P, wet grass given not rain, is substantially greater than 0, P, rain given wet grass, is substantially less than 1. On the other hand, if the grass was never wet when it wasn't raining, then knowing that the grass was wet would always show that it was raining. P, rain given wet grass, is approximately equal to 1, even if P, wet grass given rain, equals 50%, that is, even if the grass only got wet 50% of the times it rained. Evidence is always the result of the differential between the two conditional probabilities. Strong evidence is not the product of a very high probability that A leads to X, but the product of a very low probability that not A could have led to X. The Bayesian revolution in the sciences is fueled, not only by more and more cognitive scientists suddenly noticing that mental phenomena have Bayesian structure in them, not only by scientists in every field learning to judge their statistical methods by comparison with the Bayesian method, but also by the idea that science itself is a special case of Bayes' theorem. Experimental evidence is Bayesian evidence. The Bayesian revolutionaries hold that when you perform an experiment and get evidence that confirms or disconfirms your theory, this confirmation and disconfirmation is governed by the Bayesian rules. For example, you have to take into account not only whether your theory predicts the phenomenon, but whether other possible explanations also predict the phenomenon. Previously, the most popular philosophy of science was probably Karl Popper's falsificationism. This is the old philosophy that the Bayesian revolution is currently dethroning. Karl Popper's idea that theories can be definitely falsified, but never definitely confirmed, is yet another special case of the Bayesian rules. If Px given A is approximately equal to 1, if the theory makes a definite prediction, then observing not X very strongly falsifies A.
On the other hand, if Px given A is approximately equal to 1, and we observe X, this doesn't definitely confirm the theory. There might be some other condition B such that P, X given B, is approximately equal to 1, in which case observing X doesn't favor A over B.
For observing X to definitely confirm A, we would have to know, not that Px given A is approximately equal to 1, but that Px given not A is approximately equal to 0, which is something that we can't know because we can't range over all possible alternative explanations. For example, when Einstein's theory of general relativity toppled Newton's incredibly well-confirmed theory of gravity, it turned out that all of Newton's predictions were just a special case of Einstein's predictions. You can even formalize Popper's philosophy mathematically. The likelihood ratio for X, the quantity Px given A, over Px given not A, determines how much observing X slides the probability for A. The likelihood ratio is what says how strong X is as evidence. Well, in your theory A, you can predict X with probability 1, if you like, but you can't control the denominator of the likelihood ratio, Px given not A. There will always be some alternative theories that also predict X, and while we go with the simplest theory that fits the current evidence, you may someday encounter some evidence that an alternative theory predicts but your theory does not. That's the hidden gotcha that toppled Newton's theory of gravity. So there's a limit on how much mileage you can get from successful predictions. There's a limit on how high the likelihood ratio goes for confirmatory evidence. On the other hand, if you encounter some piece of evidence Y that is definitely not predicted by your theory, this is enormously strong evidence against your theory.
If P, Y given A, is infinitesimal, then the likelihood ratio will also be infinitesimal. For example, if P, Y given A, is 0.0001%, and P, Y given not A, is 1%, then the likelihood ratio P, Y given A, over P, Y given not A, will be 1:10,000.
That's minus 40 decibels of evidence.
Or, flipping the likelihood ratio, if P, Y given A, is very small, then P, Y given not A, over P, Y given A, will be very large, meaning that observing Y greatly favors not A over A.
Falsification is much stronger than confirmation. This is a consequence of the earlier point that very strong evidence is not the product of a very high probability that A leads to X, but the product of a very low probability that not A could have led to X. This is the precise Bayesian rule that underlies the heuristic value of Popper's falsificationism.